Now, Dr. Jobst Landgrebe on the quantum ontology, content and structure.
Thank you very much for having me here. So please show the next slide. So we have to ask ourselves, how do we organize all this knowledge? And I want to give you a kind of preview of how we conceptualize this and want to deal with this in the following the similar principles that we have used in the medical domain. So you see here on the left, you see on the left-hand side, basic formal ontology, widely used ISO standard, or the first serious ontology ISO standard, then also the first piece of applied philosophy ever standardized by ISO, which Barry Smith and others developed, which actually allows us to build taxonomic hierarchies of common sense reality. So it's used for positive science, but it contains only entities which also have individuals, like tree and this individual tree. Then we have physics, physics has another component. It not only needs common sense reality entities, but it also needs the part of reality that is modeled using physics. So it contains universals and also entities from mathematics. For example, a typical physics-specific entity would be a unit of measurement or a magnitude. On the right-hand side, you see mathematics, which contains the ideal entities in their structures, like the number pi or other ideal entities that don't have instances in reality. And so the ontologies of physics use the physics upper ontology and the mathematics upper ontology, for example, classical mechanics or quantum physics, as you see it on this slide. So you see here that physics relates via multiple relationships to the common sense reality, but also to mathematics. On the next slide, you see how how physics is structured. So basically, physics always contains theoretical physics and mathematical entities with the axioms and hypotheses. Then models, which is the core of physics, which are propositions that basically mediate between the hypothesis on the top and the observations from reality on the bottom. And at the bottom, we see observations from reality. On the right-hand side, you see the inference pattern, the famous pattern that was one of the key experiments, the double-slit experiments that led to quantum mechanics. And so you need also, as part of a theory in physics, a successful model application to observations. For example, in general theory of relativity, that was the measurement of a few years ago in 2015 of the gravitation wave, which is modeled on the left, or in quantum mechanics, a double-slit experiment. So in our perspective, the string theory is not a theory because it doesn't have observations that confirm the models. On the next slide, now we see how physics, the ontology of physics is really built up. So on the left-hand side, we always have a system which is a real, mind-independent but human-delimited set of entities which are interrelated. For example, here I've put as an example the weight on a spring, which is of course also a material entity. Then in the middle we have the magnitude which are needed to measure observations in reality, like mass, time, distance, or retraction. Retraction is needed for the weight on a spring. And then we have the model, which is of course an ideal and mind-dependent entity. And here, for example, we have the force oscillator with dampening, which is one of the most important models of classical mechanics, which models the weight on spring. So here you see now how it becomes possible to organize the entities of physics in a perfect way, so that there are no misunderstandings, that it becomes totally clear what they mean, and that also different scientific communities can interact. And at this level, of course, of textbook physics that I'm showing here, of beginner physics, it's very easy, but it gets very complicated if you go one level down. So on the next slide, we now see, so how will the structure, the quantum ontology be structured? It will have 3 layers. On the top layer, there will be the physics and mathematics upper ontology, which is already quite far developed. So Barry and I have been working on this the last 1.5 years. Then you have in the middle the quantum physics ontology, which contains quantum mechanics, quantum field theory, quantum electrodynamics, and so on. So the real tough theoretical stuff. And then you have what is, of course, at the core of your interest, the quantum engineering ontology, which contains quantum computing, quantum devices, and so on. And now how do they hang together? We see this in the next slide. We see here an example. The magnetosensor, which Charles mentioned among his zoo of terms, there was also magnetosensor. This is a very classical one, the SQUID, which was invented in the 60s. You all know this. It's what you learn in every quantum mechanics course. You know that the current that is produced by the SQUID is proportional to the magnetic flux. And when the magnetic flux exceeds flux quantum, then you have an oscillation of the induced current. And this way you can measure extremely weak magnetic fields. And that was one of the first quantum devices. I mean, no, not the first, but it's a very interesting quantum device. And it contains, to understand it properly, you need to have a lot of knowledge of quantum physics and quantum electrodynamics. And it's also fascinating because it's, of course, a macroscopic quantum phenomenon. And so how can we put this into an ontology? Now, this is shown on the next slide, which shows you again the upper ontology that I described at the beginning. So we have the physics entity made of systems, magnitudes, and models. And now we see that the SQUID is actually a type of superconductor. So a superconductor is a type of a system. A Josephson junction is, of course, what is needed to build a SQUID. And the SQUID is then a device that is made, I mean, it's not only made of Josephson junction, but it contains two Josephson junctions. Then the magnitudes here, they are not complete, but you see at the bottom, you have here under magnitude, the quantum wave phase and the magnetic flux, which are two magnitudes that you need to understand the SQUID. On the right-hand side, you have the mathematical model. So at the top, you have the quantum mechanical model. Then, of course, the Schrödinger equation. Below this, you have the macroscopic quantum phenomenon, like superconductance. And then the Josephson effect, which is also a type of macroscopic quantum phenomenon. So from this example, you can see how all the entities that are used in a quantum engineering field, such as the SQUID, can be introduced into the ontology in an elegant way to make everything clear and interoperable and interchangeable, and also to measure how fields evolve, to speed up comparison of fields, to allow AI algorithms to mine and automatically annotate abstracts from scientific papers. And so there are many ways to use this. And here you see, based on a simple example of the SQUID, how this can be put into a physics ontology. I think that's it, and I am happy to take questions later on.